Thank you so much for the introduction and for the AV help. So we've heard a lot of talks about algorithms, reconstruction algorithms. This talk will be a little different. So in yesterday's talk and today's talk, we heard about algorithms that can sample from the posterior distribution. This is a property that's very exciting for us technical folks, but radiologists are not really trained to integrate this kind of information in their decision-making process. So today I'm going to talk about an observer study we designed to try out some new display methods to communicate information from the posterior to radiologists. So before I start, I'd like to thank my lab, the Impact Lab from the University of Pennsylvania. This work is supported by funding from the NIH. This is also a multi-institution collaboration with collaborators from UPenn, Johns Hopkins, and UT Santa Barbara. I'd like to thank all the collaborators for contributing to this work. So in recent years, deep learning reconstruction has exploded in popularity. There are a lot of advantages to these algorithms. Some great examples we have heard in this workshop. They can transcend traditional signal-to-noise trade-offs and produce high-quality reconstructions, even with very low-quality measurement data. They're fast to compute, and they can solve problems that are traditionally very challenging to solve. They're also capable of producing beautiful looking images. A lot of these images can appear noise-free with high spatial resolution and with minimal artifacts. However, there are also a lot of challenges with deep learning reconstruction. These regions of high noise streaking artifacts, they traditionally serve as visual cues for radiologists to indicate which area of the image has good quality and is more trustworthy. And these visual cues can be absent in some of the deep learning reconstructions. And the image may look realistic anatomically. However, they may contain fake structures that's not supported by the data or that's not in the ground truth. And these are problems of hallucinations we all are very familiar with. There are also concerns with generalizability of these algorithms when applied to data that's outside the distribution of the training data. And a lot of the traditional kind of network architectures are used as black boxes and lack interpretability. So in recent years, a new class of reconstruction method, diffusion posterior sampling, or DPS, has emerged as a very promising approach that can potentially address some of the issues I mentioned earlier. So we heard a lot about diffusion models and DPS in particular, from Webb and other speakers. So just a very brief recap of how DPS works. As the name suggests, DPS uses a diffusion model to capture the prior distribution of an image class, in this case, CT reconstruction. In the forward process, we use a stochastic process to gradually add noise to the image and gradually fade the image signal away until we arrive at a pure noise on the very right. Okay. And then there exists a reverse stochastic process where we can gradually denoise, so going backwards until we arrive at a sample from the prior distribution. So the critical piece in this model is the pink term, which is the prior score function, which is the gradient of the log of the prior distribution. And this is learned using a neural network. So this model is purely generative. In diffusion posterior sampling, or DPS, we're replacing the prior score function with a posterior score function. So instead of having an unconditioned process, we're conditioning the reverse process based on measurement data Y. So now we can again take the same kind of discrete steps in a reverse process and arrive at a sample now from the posterior distribution instead of the prior distribution. So this is the first nice property of DPS. We can produce samples from the posterior. Using Bayes' rule, we can also split this term into two terms, into the log likelihood term in pink and the prior score function in orange. And this equation can already reveal several other advantages of DPS compared to traditional machine learning methods. First of all, it has the log likelihood term, which uses our knowledge of imaging physics and data statistics. And I think I'm preaching to the choir here in saying that by integrating physics in the model, it adds interpretability to the model compared to kind of pure data-driven methods. The second advantage is that we can train the prior score function once and apply any measurement model we want. Well, that's, I guess, that's based on measuring data that's drawn from the prior. So this allows the DPS method to be generalized to imaging conditions, a wide range of imaging conditions. And third, we can also tune the relative weight between the log likelihood term and the prior score function to control image property. So in other words, we can control how much we want to rely on the data and how much we want to rely on the generative prior. So the type of image quality trade-off we're observing is very different from the traditional bias variance trade-off we get from model-based reconstruction. This is a little hard to quantify, but it's still an improvement compared to the kind of one input, one output deep learning models. So I want to talk a little bit more about posterior sampling. So here I've reproduced the update equation of DPS on top here and include a very cartoonish, simple representation of the terms we just talked about. Of course, in reality, these distributions are very high dimensional and much more complex than the doodles I'm having here. So the log likelihood term is something we're very familiar with. As an example, I'm including the log likelihood of a Poisson random variable, which projection data in CT, in the ideal case, can be modeled as Poisson random variables. In traditional model-based reconstruction, we can use very simple priors with analytical forms. So for example, this is a commonly used smoothness prior. We can combine the likelihood and prior to form an objective function and use some sort of optimization algorithm to arrive at the maximum a posteriori or MAP solution, which is basically the estimate that maximizes the posterior distribution. For DPS, however, the log likelihood stays the same. The prior is now learned with a deep learning model. We also don't really have an explicit objective function because we're using this kind of alternating update approach between likelihood update and score function update. So instead of arriving at the MAP solution, we instead have samples from the posterior. So just to give you an idea of what posterior samples may look like, on the slides I'm showing different samples of DPS reconstruction of a thoracic CT slice at different dose levels. So a couple of observations jumps out. So first of all, as the dose decreases from right to left, the image becomes more generative and there's more variability. And this makes sense, right? Because when the dose is low, the relative weight of the log likelihood is lower compared to the generative prior. So we're more reliant on the generative prior image. The type of variability we're observing is complex, is very different from kind of the stochastic noise variations we observe with traditional reconstructions. And the type of variability is structural. And we see that some structures still persist in the image, even in the very low dose case. And this is an idea we still need to explore further, but we believe that this kind of variability, which features are more variable, which features persist through multiple samples, may give us a sense of whether these features are hallucinations or real and supported by the data. So now we have an algorithm that can draw samples from the posterior distribution. A natural question that arises is, how do we use these posterior samples? First, we want to recognize that the purpose of performing reconstruction is to complete downstream tasks. So we're really interested in the integration of the posterior in the space of hypotheses. So we frequently simplify, the simplest form of imaging tasks is binary decision making. So for example, the binary decision may involve, is a signal present or is a signal absent, or does the lesion have feature A or feature B? So the decision-making process can be modeled as the observer internally computing a decision variable and comparing it with a decision threshold they have formed during their training or using some sort of risk assessment. By comparing this decision variable with a threshold, if it's greater than the threshold, they will make one decision. If it's less than the threshold, they'll make another decision. So if we can have machine observers that can completely kind of grok the posterior distribution, the answer is easy. We can provide the posterior distribution to the machine observer and essentially approximate an ideal observer that can achieve maximum possible performance. Of course, we don't really have the entire posterior distribution. We only have samples of it, but that's okay because there are previous work training machine learning observer, deep learning observer using kind of multiple realizations of the anatomy, multiple realizations of the imaging task, and show that this kind of observer can approach ideal observer performance. However, a lot of the clinical decision-making process still relies on human observers, and human observers are not ideal. In fact, we're very suboptimal observers. Radiologists are also traditionally trained to just read one image sample, especially in CT. So if we run DPS once and present a random sample to the radiologist, we can get very unlucky and lead to a wrong decision. Even if we can choose an optimal sample, it's very likely that what's the optimal sample depends on imaging task. And in very complex clinical scenarios where radiologists needs to make multiple decisions, it's very unclear what is the optimal sample that we should present. And it's likely that presenting multiple samples to the radiologist are beneficial. So the central goal of this investigation is really to answer two questions. First, can radiologists take advantage of multiple posterior samples? And also, what is the best way of communicating information from the posterior to the radiologist? So to answer these questions, we designed an observer study. First, I want to go through data generation. So we're focused on kind of lung CT imaging. So for ground truth, we used lung CT images from a public database called the Lung Image Database Consortium, or LIDC, as the ground truth data. To generate the measurement, we forward project the ground truth, inject independent Poisson noise. The noise level, or the dose level we're simulating, has a bare beam fluence of 10 to the 3. So for reference, this is a very low dose level that's 1 to 2 orders of magnitude lower than normal dose lung CT scan. We were focused on a very specific binary decision task. This is a discrimination task. We want the observer to tell whether the lesion has a spiculated boundary or a non-spiculated boundary. So for those of you who don't know, spiculation is when there's like spiky processes coming out of the lesion, and that's typically associated with malignancy. So we chose the data we want to use according to lesion features annotation that's already provided with LIDC. So this is a very nice feature about LIDC. It already has a bunch of feature annotations provided by up to 5 radiologists. So for spiculated lesions, we chose 100 cases from the pool of lesion. The public annotation have kind of designated as spiculated, and for non-spiculated, we chose another 100 cases. So there are 200 cases in total. We want to exclude small lesions where we don't really have the spatial resolution to distinguish boundary features, so we limited the nodule diameters to between 10 and 30 millimeters. And for this study, we're only using a 2D slice instead of a 3D lesion volume, so we need to choose an axial slice from the lesion volume. We did this by computing a particular radiomics measure called speculation index. So for speculated lesion, we chose the slice that has the maximum speculation index. For non-speculated, we chose the slice that has the minimum speculation index within the lesion volume. For reconstruction, we did 2 types of reconstruction. One is good old FBP reconstruction, and the other is diffusion posterior sampling. And for observers, we recruited 4 very brave radiologists from Johns Hopkins and University of Pennsylvania who are willing to try out these new display methods. And the observer study we designed is a receiver operator or characteristics, or ROC study. So we present 1 lesion to the observer and ask them to pick one of 5 graded responses, from definitely non-speculated, probably non-speculated, equivocal, probably speculated, to definitely speculated. So the reading order, so the 200 cases are randomized for each observer and each display method we tested, which we'll talk about later. The lesion is always at the center of the ROI, and we tell the observer this information. So this is not a search task, not a detection task. We're asking them to solely focus on the feature discrimination task. And we're presenting them with a small ROI that's about 6 centimeters in size. So in addition to their responses, we also record the time taken for each case by each observer. And this slide illustrates the different display strategy we tested. So first, we have a kind of low-dose FBP reconstruction as a baseline. We also showed them just a single random sample of DPS reconstruction. And we also tested displays that show multiple posterior samples. So there are lots of information we can display to the observer from the posterior distribution. We can, show standard deviation, we can show covariance, we can compute moments from the distribution. But we thought for starters, let's start simple and show them just image samples using display formats they are familiar with. So these bottom two are the two multiple sample display methods we did. So we generate 30 DPS samples and stacked them in a movie format where they can scroll through. So, radiologists are used to scroll through 3D volumes, but now instead of scrolling through the volume, they're scrolling through different posterior samples. So our hope is that by scrolling through these image stack, they can build up model of the posterior in their brain, and appreciate that features that persist have higher probability, features that vary a lot have lower probability, and our hypothesis is that they can integrate this information in their decision-making process. The second type of multi-sample display we tried is this tiled display. So we used the same 30 samples, but then placed them in the grid of 5 by 6. So this is also a display method that's familiar to radiologists in nuclear medicine. And just to give you an idea of the kind of image quality the radiologists are presented with, here I'm showing low-dose FPP, a single sample FPP, single sample DPS, a movie DPS showing the kind of variability we're talking about, and also a high-dose FPP for reference for an example lesion. So low-dose FPP is very noisy as expected. Single sample DPS is much less noisy. We do see a lot of variability in the movie DPS. So the variability shows up for both the lesion itself and the surrounding parenchyma. And we did tell the radiologists to try their best to ignore the kind of parenchyma variation and just focus on the lesion only. So at the bottom of these images, I'm also including one radiologist choice for these cases. So for single sample DPS, they chose this as probably unspeculated, but when presented with the movie DPS, their ratings have changed, definitely speculated. And this is a case when the movie DPS annotation agrees with the ground truth, which is also speculated. So this is another example showing the type of image quality. And again, here for single sample DPS, they chose definitely unspeculated. For movie, they changed their rating to probably speculated. And this case also agrees with the ground truth. So this slide shows the ROC curve for each radiologist and for each display methods. The AUC for each ROC curve is displayed in the bottom here. So a couple of observations. The low-dose FPP has the lowest AUC as expected. For reader 2, 3, and 4, the movie display method has the best performance. For reader 1, however, the tiled display method has the best performance. Another very interesting observation is that for reader 3 and 4, the tiled methods actually perform worse than the single sample method. And for reader 1, the movie method performs worse than the single sample method. So this is very interesting because the same amount of samples, the same exact image is actually used in the movie versus the tiled. But how they're integrating this information is very different and is very reader dependent. And this slide shows the ROC for all readers pooled. Again, low-dose FPP has the lowest AUC, so AUC values are shown here. The single sample DPS has a slightly higher AUC. Both multi-sample display, movie and tiled, have higher AUC. To show the statistical significance, I'm also showing the p-value for pairwise comparison of these 4 strategies. So we see that the low-dose FBP, in fact, is the single sample DPS is in fact not statistically significantly different from low-dose FBP performance. The movie DPS does perform better than low-dose FBP, and so does the tile DPS method. And comparing single and multi-sample display, so we're looking at kind of 2 versus 3 here, we're getting a p-value of 0.078. This is not, less than 0.05 like we expected, and this suggests that including more readers may be beneficial for our future studies. So we also recorded the time taken for the observer to read each case, and the results are shown on this slide. So the bars shows the average number of seconds taken for each case for each display methods, and the green line shows the standard deviation. We also capped the time at 60 seconds because they're doing the study remotely and there may be connection methods, they may have left their workstation to do something else. So any time that's greater than 60 seconds, we just capped it at 60. So we see that the multi-sample display method does take longer to complete. On average, it takes 30 to kind of over 100% longer than single sample method. However, which strategy takes longer and how much longer it takes is also dependent on the observer. So we're still at the beginning stage of this investigation, but we have learned a lot of interesting things from this investigation. I think the results suggest that radiologists are able to interpret multiple posterior samples, and using multiple samples, the performance is better compared to single sample methods. What's interesting is that how multiple samples are displayed, so movie versus tiles, does affect performance, but the optimal display seems to be reader dependent. And as expected, it takes longer to read multiple samples, on an average 30% to over 100% more, but how much longer is also very reader dependent. So for future work, we plan to extend the study to include 3D lesion volumes, recognizing that a lot of the lesion features are better appreciated in 3D. And as I mentioned before, there are a lot of other information we can display to the radiologists, like uncertainty maps, which I believe Jacopo will talk about later. We also plan to expand the study to more clinically realistic tasks. In addition to speculation, there are other lung lesion features that are important for diagnosis, like calcification, solidity. We also plan to expand the study to include elements of search and detection. So that concludes my talk. Thank you so much for your attention.
So very interesting. So since your data set, you have the lesion in the center of the image, so I think that this data set is directly applicable to like channelized Hotelling observer or some other mathematical observers. Just curious if you have tried that, this data set.
Right. Developing mathematical observers is definitely an area of interest. So we would love to look at this in the future. So I think even when the lesion is not centered, there are still observer models that can describe search and detection. So this is definitely an area of interest.
Thank you.
Very rigorous work. I have two questions. One is that for engineer like us, we like to see the uncertainty and generate a bunch of images, but the radiologists, they have different view, right? Yeah. So in the last 5 years, the number of images that radiologists read tripled in the last 5 years. Yeah. So when I present the similar things to our radiology, they say, no, we don't want to see more images. Give us one simple image. We don't want more. So what's the feedback you get when you do the observer study with the radiologists? And is there any smarter way to present this information in one image to the radiologist? That's the first question. Yeah. The second question is that I actually don't worry that much about posterior distribution. I'm worried about prior distribution. So we all generate the image and then we say, wow, that looks like a real image, it's really cool. But nobody has checked whether we actually generate the right distribution of the prior distribution. Give you an example. If we look at any given disease, I bet the distribution of the prior distribution is a long tail distribution. Likely when we generate that prior images, we generate something towards the center of the distribution. If you do this, then whatever prior distribution generated is going to be biased to the center. So it's not fair for this non-tail distribution that samples. So have you looked at your prior posterior distribution, whether it can give you right distribution for some long-tailed samples in your prior distribution? Have you checked like the samples you generate? I'm just curious.
Yeah, both are great questions. I guess I'll start with the first question. Yeah, so breeding more images is definitely not a welcome kind of task for a radiologist. We can think of more efficient ways to display even multiple posterior samples. Instead of asking the radiologist to read through 30 image volumes, we can imagine they can scroll through a single image volume, and if they find somewhere that's suspicious, they can bring up another window where we can display kind of more posterior samples in that way. So that in somewhat can avoid the problem of reading multiple image volumes. Our radiologists have been very welcoming of the idea of improving performance, and that's kind of the task we're focusing on. Can we improve performance compared to a single sample? There is the question of how many samples is enough, because that's going to directly affect how much time the radiologist would take to read these images. And we kind of arrived at this 30 image sample as a pretty kind of lucky compromise between reading time and how well it's able to capture the posterior distribution. But I can also imagine there's optimization to be done in terms of how many samples to present. I would think it's very likely dependent on the imaging task, depending on the data. So there's definitely further refinement in that area. The second question, the long tail distribution, that's a great question. It applies to rare diseases, for example. But I think that's where the ability to use the data or rely more on the data becomes more important. The training data we're using for the EPS method here is drawn from slices in CT, in public CT databases. So I think more likely than not, more slices are healthy compared to unhealthy slices. We're at least still able to reconstruct lung nodules, so I think that's encouraging, but this is definitely something we should pay more attention to in the future.
Yes, thanks.
So take a online question from Satish. Have you considered trying to quantify hallucinations? Was that ever raised as a concern in your observer studies? And if so, how might you go about quantifying hallucinations or having observers rate images on hallucinations?
I think that's a great question, and a question that is still very much an open question that deserves a lot of research. I'm not sure I have a very short answer to that question, so I'll just say it's a very important direction I'm very interested in, and definitely the whole imaging community is very interested in. Yeah.
Okay. Thank you, Grace.